All right, today we're talking about spheres. We're talking about specifically the surface area and volume of a sphere. So first of all, a sphere is just analogous to a circle, but it's in 3 dimensions. So the way we define a circle in 2 dimensions is it's the set of all points in a 2D space that are equally distant from a given point. So if I put a pink dot here and give a set distance, let's say 3 centimeters, I could draw every point that's 3 centimeters away from that center, and once I draw those infinitely many points, it would form a circle. That was a perfect circle. Now we define it exactly the same way, except we just say now in 3D space, the set of all points equally distant from a given center point is a sphere. We use all the same vocabulary. We still call the center a center. We have a radius, a chord, a diameter, a secant, a tangent, all the same words that we used with a circle. We're just analogously using them in a 3D space now instead of a 2D space. Okay, so just a note on drawing a sphere. We don't draw a sphere as a circle. Okay, that's a 2D circle. If we want to give it 3 dimensions, we start with a circle, and then we draw another 90-degree perpendicular one. So it's like taking this screen and rotating it 90 degrees. So now it's sticking straight out of the screen and straight into the screen. And you can see that in all of the images here, right? There's an outer circle, and then there's this 90-degree perpendicular circle to that. And it's coming out of the board and going into the screen. You can see by the dashed line that's in back. And again, that's just quick. Draw one like this, and then here's coming out towards us. And then here's going in behind it, and then draw a center point. And there's my sphere, okay? So, 2 vocab words we're going to be using here. Hemisphere means half of a sphere. Comes from the same root as demi or semi or hemi. All 3 can be used to mean a half from the Latin roots. So, I don't know why they chose hemisphere instead of semisphere or demisphere. But hemisphere is what we use to talk about a sphere that's been cut in half through the center. And then finally, the other one is a great circle. So a great circle is simply saying this is the biggest circle that you could draw on the sphere. We could start like thinking about if I'm at the North Pole of this hemisphere up here, I could draw a little teeny circle walking around it, right? Just like walking around the North Pole. I could do a little 1-foot radius circle. I could, be down a little lower towards Canada and the Arctic Circle's edge. I could, again, walk a bigger circle or fly or, so on. And then I could go lower and lower towards, North America, Europe, and Eurasia and go around and fly. And again, this flight is getting bigger and bigger each time, right? As I get closer to the equator now, maybe I'm in Central America, goes all the way back. Now I'm getting really close to the equator. My circle is still getting even bigger. And once I get onto that equator, that's going to be the biggest circle I can create. And its center is the center of the sphere. And then if I go below the equator, now I have a smaller circle again. And I loop back, smaller circle as I go down even lower than that until again I'm around the South Pole there. It's a little circle. So the biggest possible circle is essentially the equator, although it could be in any direction. So down here I drew 3 different great circles in 3 different directions, but the biggest thing is it's the largest possible circle you could draw, and its center is the center of the sphere. So it just goes all the way around the sphere. Okay, so using those 2 vocabulary words and all of the information we've done with circles, let's start applying it, okay? So the surface area of a sphere is just 4 pi r squared. This is one of the things I love about math, that it works out so perfectly. 4 area of a circle. Exactly. Not a weird decimal, not a sloppy, crazy derived, but exactly 4 circles. Why? I don't know. I've never had a great explanation of this. We could derive it with calculus, but still it's just steps and problem solving, and poof, you get exactly 4 once you solve for it. But the conceptual, how you could like cut it and wrap it, I've never heard a good one. But think about that. That means if I take a sphere here and I cut it and cut it, so now I've got essentially like a, quarter of a watermelon or of an orange or something. So you think about it in the back. If I've got that wedge, each quarter wedge has exactly 1 pi r squared as its outer surface. 4 of those together is 4. So why is it exactly 4? That's just beautiful. Anyways, so it's a formula that we can apply. That's the surface area, the 2D surface area to cover. So here we go. If we want to find the surface area, well, first one we'd say the surface area is 4 pi. The radius is 4, so it'd be 4 pi 4 squared. And multiplying that together, we get 64 pi, right? And that'd be in square feet because it's a 2D area. When we go over to a problem like 5, where it gives us a diameter, we'd say, okay, well, first thing, let's know that that's the diameter. So dividing it by 2, we get 9.15 as the radius. And then we use that. So we say, okay, 4 pi 9.15 squared would be our surface area, right? And you could do that on a calculator, but that's how you would set it up. Again, because 9.15 is exact, you could say I have 4 times 9.15 squared. That was not 9.15 squared, so 4 times 9.15 squared. And we get 334.89, so this is 334.89 pi, right? Okay, so that would be an exact value, just multiplying that together. So let's scroll down here and see what was the error here. So describe and correct the error in finding the surface area of the hemisphere. Okay, well, looking at this, they use the surface area of the whole sphere, 4 pi r squared. So let's see what's wrong with that. Well, if I take a sphere that has a surface area 4 pi r squared, and I got to draw this 3D, not 2D. And then what I do is I slice it with a plane here, right? And just cuts right through here. I intersect with this spot, just shoom. Then what I've now got is I've now got this top half. Okay? Where this part is now 1/2 of 4 pi r squared. So I've got 2 pi r squared, okay? You could kind of think about this as like the lateral area. Although with a sphere, all of the outside is a lateral area. But the difference here is, so you could say, okay, well, the mistake was they should have used 2, right? But be careful here. And this is where this gets a little ambiguous when I say the surface area of a semisphere or hemisphere. Is, are we counting the bottom? So in this one, since we sliced it in half, yes, that half of the outer sphere has an area of 2 pi r squared. However, there is now a base that's exposed. That now counts as surface, and that base is a circle, so we need to add a pi r squared. And so when we bring those together, we get that 2 pi r squared plus the pi r squared, where this is kind of, you could think about this as like the outside and this as the base. And so together they total 3 pi r squared. So actually a quick response is they should have used 2. That's half. But when you think about bringing in that base, they should have actually used 3 pi r squared, right? There's 2 of the pi r squareds up here. And then there's 1 pi r squared on the bottom. So when I said this is ambiguous, if we say what's half the surface area of a sphere, it is 2 pi r squared. But that's just for this outer top lateral area, if you would. And then that base is another pi r squared. So know whether you're including it or not. If we say what's the surface area of this hemisphere, since the bottom's exposed to air, we count it. If I said what's the area of a cylinder with a hemisphere on top, well, then we would only count that lateral area, or the 2 pi r squared, and there would be no base. Okay. All right. So now the volume of a sphere. Now this is going to be much more interesting, and I'll try and reason this out for you why this is. So it's 4/3 pi r squared, or pi r cubed, and I'll say the mistake is the one I just said. Is the mistake here is that a lot of people just interchange the squared or to the third, as I just slipped up, right? Is they do r squared versus an r cubed. So just know this is a 2D surface area. This is a 3D volume. That's the easy way I remember it. This is things like inches cubed, and this is things like inches squared. So that's a common mistake between the two formulas. People switch up the powers of R. But let's look at why this is true, okay? Now, if you want to skip this why and go straight to the problems, you can skip ahead a little bit. But I want to talk about this. So one way in which we can find the area of a circle is you could say, well, this isn't really a circle. It's a lot of little slices where each of these slices is a triangle. And you say, okay, well, let's lay all those triangles out. So it'd be, they look like this as you lay them all out. And we know that if you take a triangle with the base and some, height, and we slide the tip left or right, well, since the area is just 1/2 base times height, it doesn't matter whether you slide it to the side. If it's got the same height, it's got the same area. So, okay, we can slide the tip side to side as long as we don't make it taller or shorter. So what I'm going to do is I'm going to slide all the tips of these triangles together, right? I'm just going to put them all together into a single point here without going up or down, just side to side. So now what I've created is one single triangle out of all these different slices, right? And so this single triangle I've just created, well, what's the base here? Oh, let's look at this. If we add up this plus this plus this, so all the bases of all the triangles, we've now gone all the way around the circle. So this bottom part where we add all the bases together is the circumference of the circle, or 2 pi r. And well, what's the height of this? Well, the height of this is the distance to the bottom of the triangle from the center, right, for any one of these. And perpendicular to that tangent line, that base there, we get that this is a height of r. So we say, oh yeah, well I know the area of a triangle. It's 1/2 base times height, or 1/2 the base, which is 2 pi r, times the height, which is r. And so look what we get. We get 1/2 times 2 pi r squared, or we get pi r squared. So that's a way we could find the area of a circle. So now think about this. Now this is cool. What if I said a sphere isn't really a sphere? It's actually just a bunch of pyramids. So if you chop it up into little tiny pieces, each one of which is a pyramid, and it's like digging your thumbs into an orange or a little cutie, and you split it open and out come all those wedges, right? If we unwrap this, we get this surface here, and each one has a little pyramid sticking out, and this is in 3D here, right? So we have all these pyramids sticking out. Well, think about it. Again, same thing, right? The volume of any, I mean, let's stop for a second. Before I get too crazy in this, you'll be like, what are you talking about, man? You're crazy. Like, this is a curve. It's not flat. Like, this doesn't happen. Okay, well, I beg to differ. In nature, this happens all the time. When you have curved things, it's very often that the way we deal with that is by flat objects, right? Flat planes or lenses all put together to create this curve, right? Whereas locally, each one of these is flat. And we could zoom in and see again, you get all these little shapes. And again, we zoom in even more and we get all these little shapes, right? Kind of like little hexagon looking things. So the reason I mention this is this happens all the time in nature. Oh, that's just a beautiful picture, right? And it is true that at a local level, as we take a small enough slice, it is flat. You're like, no, it's curved, it's curved. And I'd say, oh, really? Okay, so the room you're sitting in right now, is it curved? Is your, desk chair rolling to the side? Is your pencil rolling off your desk? No, on a local level, if you take a small enough slice, it's flat, right? I want to set a flat foundation for my building. I want to set a flat walkway from one building to another so I can walk on flat ground. And locally, things are flat. It's only on a larger scale from city to city that we have spherical geometry. When you're traveling from here around the planet to somewhere else, that is a curve, not a straight line. So when you're talking about air traffic control, like what airlines do, we're talking around a sphere, the planet's moving, wind, and that's a whole nother ball game, right? But on a local level, we can use flat 2D geometry. So let's see how we could actually use this then. So what we've got is we've got all these pyramids here, right? And we know the volume of a single one of those pyramids is 1/3 base times height. Now again, since, if they have the same height, just like with a triangle, we could slide all the tips together, not changing the height at all, but let's slide them all together into some center point. So now what I have now is all the bases of the shape side by side and one center point here. So I got this crazy polygon where I have this, it's essentially this amalgamated bottom of all the bases going to a single tip. So this is just another pyramid. So its volume is 1/3 base times height. Well, let's think about this. The height of every single one of these was just the distance from the outside to the distance to the center. So, of course, the height here is R. And then what's the area of the base? Well, the area of the base, this is just the surface of the sphere that we opened up, right? This is the orange or tangerine that we opened up. And we know that that's 4 pi r squared. So let's just put that in. We get 1/3. The surface is 4 pi r squared times r. And you can see we get 4/3, 4 times 1/3, and then pi r cubed. So really this wasn't a sphere, it was just a lot of little pyramids all pointed into the center. If you open it up like an orange, you can see, and you can just calculate the volume of that. So that's a cool little trick. Again, you could skip that part of the video if you wanted. Now let's apply it. Sorry. So find the volume of this. Hold on. Okay, so let's keep working. So we've got our new formula, right? So the volume is 4/3 pi r to the third. And again, don't mix up that r squared and r to the third. So here it gives us a radius and says find the volume of the sphere. So we get 4/3 pi 40 to the third power. And then we just go, well, let's see what 40 to the third power is. Okay, and then let's multiply that by 4 divided by 3. And we get 853. So instead of that, you know what I'm going to do? I'm just going to multiply it by 4. Oh, shoot. Let's go 40 to the third power times 4. And I'm going to leave that as thirds since it won't come out evenly. So I'm going to leave that as 256 with 3 zeros. That's how many thirds pi I have. And that's an exact volume. If you want to plug that in a calculator and approximate that, that's great. Okay, again, you could do it with a diameter. You could say, well, the first thing I need to do is I need to find the radius is half of that, or 2.5. And again, the volume would just be 4/3 pi 2.5 to the third power. And then you could just simplify that down, either as an exact answer or approximate. But anytime we tell you to go forwards, we could always have you go backwards. So I could tell you that the volume of some sphere is 36 pi. And you could say, oh shoot, well I know my formula is 4/3 pi r cubed, and I know it comes out to be 36 pi. So then we can go backwards and say, okay, well really this is analogous to some number times x to the third equals some number, right? It doesn't matter that the numbers look a little scarier. 4/3 pi is just a number. 36 pi is just a number. So I'd say, okay, if I wanted to solve this thing over here on the left, I'd just divide both sides by 2 so I could get x by itself. So I'm going to divide by 4/3 pi on both sides. Okay, so now I've gotten rid of the entire number that was there. You could do it in steps. Divide by pi, multiply by 3, divide by 4. And what you end up getting is you end up getting r third equals. Now let's do this up to the side. Let's see. The pi's cancel, and if I want 36 divided by a fraction, that's the same as 36 times the reciprocal. And over 1, I could go cancel, cancel. I get a 9 and a 1, so that's 27 over 1, or 27. And now that I've got x to the third equals a number, right, I just take the third root. So I say, okay, just like we would take the square root of raising something to the second power, we take the third root, a little 3 here, of this. And if you need help plugging in a calculator, I could absolutely help you in class, because every calculator is a little bit different. But I happen to know, and this is asking, it's asking what to the third power is 27. And I just happen to know that if you go 3 to the third, that's 3 times 3 times 3, or 9 times 3, or 27. So I just happen to know that the third root of 27 is 3 from just past experience. But you could plug that into a calculator. Okay, so it asks for the diameter. So going back and rereading the question whenever it's a word problem, I would go twice that, so the diameter is 6. Okay, so now just the last few here, we'll just, it says find the surface area and the volume of each. So we'll do this in 2 parts. So first off, it looks like we've taken this tub of ice cream and taken a big scoop out. So we're missing some volume. Let's do volume first. So the volume we're going to figure out is the volume of the cylinder to start, and then we're going to take away the volume of a half of a sphere. So I'm going to say we're going to take away 1/2 the volume of a sphere. So that is base times height for any prism or cylinder minus 1/2, and then I'm going to plug in my, in parentheses or just times, 4/3 pi r to the third. And I know the base of my cylinder is pi r squared. So there we go. I've got, oh, and 1/2 times 4, right? I could cancel my 2 and my 4 to get a 2 here. So that's 2/3 pi r to the third. And now just plugging in, well, I know that my radius is 3.3. I know that my height is 7. And so I've got pi 3.3 squared times 7 minus 2/3 pi 3.3 squared. Now, I'm not going to go ahead and simplify this with all the decimals and everything. I'll leave that to you. But that was the big picture there, is taking a cylinder and scooping out a half of a sphere. All right, on the next one, the volume is, well, this time we've got the cylinder, and now we're just adding 1/2 of a sphere. Now, it's not the same radius and same diameter, so there might be some tricks here, but let's see. So again, we've got the volume of a cylinder, prism is base times height, plus 1/2 of 4/3 pi r cubed. So again, the 1/2 and the 4/3 cancel to a 2. So we get pi r squared h plus 2/3 pi r to the third. Now the only difference here other than that plus sign is we have a new radius and we have a new height or distance between our bases. So this is pi 5.8 squared times 14 plus 2/3 pi 5.8 to the third. Oh my goodness, and look at what I did on the last problem. Classic mistake. I said it was going to happen and I did it. That should have been to the third power. See, I'm telling you, common mistakes, even for the teacher. Okay, so let's go to the next one. So here what we've got, I love volume because it's just add or subtract, right? There's no complexity of part of this, part of that overlapping. So here we've got the volume of this upside down cone plus the volume of this hemisphere. So I'm going to say volume of a whole sphere times 1/2. So any pyramid or cone, it's 1/3 the area of the base times height plus 1/2 of 4/3 pi r to the third. So this is 1/2 pi r, or 1/3 pi r squared times the height plus, now again, cancel to get a 2. So we get 2/3 pi r to the third. It gives us the radius and it gives us the height. So it's 1/3 pi 4.9 squared times the height plus 2/3 pi, and then the radius is 4.9 to the third, not squared. Okay. Now let's do some surface area here. I'll shrink this down a little bit and I'll do it in a different color here. So surface area for this one is going to be, well, we've got one base on the bottom, plus we've got the lateral area of a cylinder. So in other words, we've got this bottom. And then separately, we've got this side region here. And then the third region we've got is, and I'll draw maybe loops, we've got a half of a sphere, right? Now again, when I say a hemisphere, I mean just the outer portion, not that like surface. So again, when you find a hemisphere and you cut it in half, the question is are you just dealing with this outside top part, or are you including the base? And we're not including the base. The base is empty air here at the top. So this is plus 1/2 the surface area of a sphere. Okay, so we're going to go ahead and figure this out. But one thing I want to point out is actually 22, if you look at it, it's got a base, it's got the lateral area of a cylinder, and it's got half of a sphere. So it's exactly the same surface area. I mean, there's different numbers, but it's exactly the same surface area as 21 in terms of how you find it. The only difference is the button on top has been popped out, right? If we pop this button out, pop, it looks like this. If we push it in, it looks like this, but it's the same amount of material, same surface area, just the volume is changing by popped out, popped in. So let's go ahead and find this on 21. So the base is a circle, pi r squared, plus the lateral area of a cylinder. I know the entire cylinder is 2b plus ph. That's for cylinders or prisms. So this second part is the lateral area, separate from the bases. So I'm going to add in a ph here, perimeter of the base or circumference, plus, and then 1/2 of the surface area of a sphere is 4 pi r squared. So this is pi r squared plus, and then 2 pi r is the circumference, plus, and then we get 2 pi r squared. Now I could even simplify that with my pi r squared. It's my 2 pi r squared, so I get 2 pi rh plus 3 pi r squared. And we can actually use this same formula on the second one too. So we just need to plug in that we have 2 pi, radius is 3.3, our height is 7, plus 3 of the pi, and then this is 3.3 squared. And you would do the same formula with 22. And then for 23, let's just see the surface area would be. Let's see, so we got the lateral area of the cone, right? Just the outer portion, no base. And then we have plus half the surface area of a sphere. So that leaves us with, again, with a cone, I know it's base plus 1/2 PL. That's with every pyramid or cone. So I'm going to ignore the base and just use the lateral area. So I got 1/2 PL plus 1/2 surface area of a sphere is 4 pi r squared. So we get 1/2 2 pi r L, because the circumference of that base circle is the perimeter of the base. And then plus 2 pi r squared. So then 1/2 and 2 cancel. So we get the lateral area of the cone is pi r L. Plus, and then we have 2 pi r squared as the top surface. And you can just go ahead and plug it in, except, oh my goodness, we do not have a slant height. So we get pi, and then 4.9 times slant height, we're going to have to find, plus 2 pi, and then the radius of 4.9 squared. Now, this is a really common mistake, is that people would just use this as the slant height, but this was h. So if we want to find the slant height, we need to say, well, let's erase some things here just so it's not messy. If I know that this is 12.6 and this is 4.9 and a height and base are always at a right angle, well, then I can just use Pythagorean theorem. And so I would down here, I would say this is 4.9 squared plus 12.6 squared equals L squared. And once I find the slant height, I just plug it back in there, and then it's just arithmetic. I hope you enjoyed the video, and good luck.